Welcome to my YouTube channel and the website Global Math Institute. We'll understand rational functions, mainly how do we graph them, and we'll know all about the asymptotes. It is a lesson with grade 8 student who is doing grade 10 mathematics. You can also get ahead and beat the competition by joining my classes. Our approach, engaging students creatively, helps them to understand the concepts and connect with the learnings. You will see in this video how Abhinav understands all the concepts and connects them in graphing rational functions. Let us explore all the concepts with Abhinav. Hi Abhinav, how are you doing?
I'm doing good. How are you?
Very good, very good. So today, what do you want to learn?
Like more about holes on irrational functions?
We learned about rational functions, right? Last class.
Yeah.
Can you tell me what a rational function is?
It's basically like a quotient of polynomials.
Perfect definition. This is the best definition which anybody can give in just 4 words. Quotient of polynomials, right? So which will have a polynomial in the numerator and a polynomial in the denominator. Will it have a restriction?
Yeah, the denominator can't equal 0.
And this restriction leads to what? Can you tell me?
The asymptote,
Yes,
vertical asymptote,
very good. It leads to vertical asymptote and what? And holes. So that is the topic which we are going to cover today. So you remember exactly what we had taught last time. And this is the place where we left. This denominator being 0 can also lead to holes. And we will see how in today's lesson. Does it sound good?
Yeah.
Okay, so let's begin with very simple example. Let me say the rational function a of x is something like x plus 2 over x squared minus 4. Now, can you tell me what kind of discontinuity will it have? And first, let's begin with domain itself. What is the domain of this function?
Uh, infinity, negative infinity.
But there are restrictions. So x belongs to real numbers, but,
Yeah, but
x is not equal to what? Tell me.
0.
No, denominator is x squared minus 4, right?
Yeah, 2.
So x squared minus 4 should not be equal to 0. X squared, do not jump to conclusion. We have to really do it seriously. And so x is not equal to 4. X squared is not equal to 4. So what is x not equal to? Tell me.
2.
Plus and minus 2. Whenever you square root, you have to do plus and minus. So x is not equal to plus and minus 2. So definitely what comes here is plus and minus 2. Do you see? These
Yeah.
are the two restrictions on this particular function. And therefore, we will write that x is not equal to plus and minus 2. Now, can you factor the denominator and see it for yourself? How does it make sense? We know a of x is equal to now x plus 2 divided by what? Can you factor x squared minus 4? It is difference of squares, right? You remember difference of squares? And how do we connect that with this factoring now? Well, you could do it x plus 2 times x minus 2, correct?
Yeah.
X plus 2 times x minus 2. Clearly, you see two factors in the denominator. One of them is 0 for x equals to minus 2. The other one is 0 for x equals to plus 2, correct?
Yeah.
That explains the two discontinuities or the points where the x value is not valid for the function. Now you can see I can actually simplify it further. I can actually cut x plus 2 and x plus 2. And what do I get?
X minus 2.
1 over x minus 2, right? Now, If I simplify like this and write 1 over x minus 2, then is my function same as 1 over x minus 2? Are these two functions same?
Yeah.
No, because we have not mentioned the discontinuity. X minus 2 has only one discontinuity. It cannot be equal to 2, right?
Yeah.
So whenever you cancel, you have to write that x is not equal to plus and minus 2. Does it make sense?
Yeah.
So what have we learned? Let me just put it on the fresh page. We talked about the function ax as x plus 2 over x square minus 4, which could be written as x plus 2 over x plus 2 times x minus 2, or equal to 1 over x minus 2. Now, in moving through this, we actually cancelled in between one of the factors. However, it is very important to write that your end result does have both the restrictions, that is to say, that x is not equal to plus or minus 2. Does it make sense, Abhinav?
Yeah.
If you miss this, then minus 0.5 marks you have missed. Do you understand? Never. So we can say ax is equivalent. Both are equivalent expressions only if the restriction is included in the simplified version. Is this clear to you?
Yeah.
Okay. Now, when x plus 2 cancel, and we are writing that a of x is now equal to 1 over x minus 2, where x is not equal to plus minus 2. How am I going to graph it? That is our next question, right? How do we graph it? Well, it looks simple. It is like 1 over x move 2 units to the right, correct?
Yeah.
So you will say, well, simple as that. 1 over x move 2 units to the right. That means the graph should be something like this, right? We have learned about sketching these graphs in the last class. We'll continue exploring more, right? So we have this graph, and clearly that is our graph for ax. Well, wait a minute. This line does tell us that x is not equal to 2, which is here, right? However, the second restriction, which is x is not equal to minus 2, what happens at this point? How will you incorporate that in your graph? X is also not equal to minus 2. If I put minus 2 here, let us say if I put minus 2 here, what do I get? I get 1 over minus 2, which is minus 1 over 4, correct?
Yeah.
But this value is not on the function, and therefore we will put a hole there, a discontinuity, and we'll label this as minus 1 over 4. Do you see that? So we actually have a hole at minus 2 minus 1 over 4. Do you see that? So that is the visualization of the hole. So what we notice here is that if there is a common factor in numerator and denominator, then it leads to a hole. This makes sense.
Yeah.
So the denominator was initially 0 at this point. However, there was a common factor which cancelled away, leaving a hole on the graph. So this graph is actually similar to 1 over x minus 2 with an additional restriction that it has discontinuity at both plus and minus 2, correct?
Yeah.
Now, we'll take more examples, move forward. So let's say second function, b of x is now equal to x plus 1 times x plus 2 times x minus c. I'm just writing factored form. It is easier for us to analyze. Is it okay?
Yeah.
X over x plus 2. Let us see. Okay. Now, can you simplify this and write down the restrictions on the function? Tell me, what is the simplified version of b of x?
Okay. I got x plus 1 times x minus 3 over x.
Restrictions, if you may forget, then you have lost 0.5 marks, right? So x is not equal to what?
0.
And minus 2. Do not forget to mention perfect. And now we will write. It has a vertical asymptote, right? Which type of an asymptote? Let me write down once again, vertical asymptote, right? At x equals to 0. And it has a hole at x equals to minus 2. Do you understand? Because it cancelled that factor. Do you get the idea?
Yeah.
Perfect.
Yeah.
So this is very important to understand. All these rational functions, if they have any of these rational functions, if they have a common factor in numerator and denominator, it cancels and it leads to whole. Correct?
I have a question.
Yes.
So how do you find the whole if if like the canceling factor is like, let's say 3x minus 4, how would you find the whole then?
Okay, we'll do it. So Cx, tell me the equation. You want 3x minus 4, right? To be a common factor. Do you see that? This is what
Yeah.
you're saying, right? You multiply by anything else. Let us say x plus 1. Is that okay?
Yeah.
Now, clearly, what is the restriction in this particular case? Denominator not equal to 0 means x is not equal to 4 over 3, right?
Yeah.
Perfect. So as you can see, this cancels and we can write c of x as equals to x plus 1, just a straight line. But is c of x a straight line? With
No.
a modification that x is not equal to 4 over 3. Can you sketch this function now, Abhinav?
Yeah.
Sketch and tell me how will it look like?
Okay. So it's like it's like a diagonal line and there's a hole at 4 over 3.
What is the value?
Uh, 1 and 4/3. 4/3 and 1 and 4/3.
Yes, 1 plus 4 over 3. Yeah, 3 plus 4, 7 over 3. Correct? So
Yeah.
this is 7 over 3, and that is a whole at 4 over 3. Does it make sense? So
Yeah.
it is a straight line, as you said, with a slope of 1, y-intercept of 1, and a whole at 7 over 3. Correct? So it has similarities and it has differences between the two. Correct? Now look,
Yeah.
the graph of a rational function could be a straight line. Do you see that?
Yeah.
Graph of a rational function necessarily will not be a curve. It could be a straight line, as you have seen, correct? Now, another important question here is, will the graph of a rational function always have a discontinuity? Think and tell.
No.
Give me an example.
Like, so like, let's say like x plus 1 over like 2x plus 7. There's no common factor there.
No, but discontinuity is there, vertical asymptote. Will the
Yeah.
graph of a rational function will the graph of a rational function always have a discontinuity? We are saying a rational function is of the kind numerator divided by denominator, both are polynomials. So we are saying d of x should not be equal to 0. But
Then
could you give me a counter example? The statement is false. Counter example, please. How about this? If I have x squared plus 1 in the denominator, then will it be ever 0?
oh yeah, no.
Never. X squared plus 1 both are positive, right? So it is always greater than 0. And therefore, it never crosses the x-axis. And therefore, its reciprocal will never have a vertical asymptote or a discontinuity. You get the idea?
Yeah.
So here, we have all real numbers. So the domain for this particular function is x belongs to real numbers. Makes sense, right?
Yeah.
Clear. Now, let me sketch such a function for you. And let's say e of x, we said, is equals to 1 over x squared plus 1. How will I sketch this function? Can you please help me in this sketch? This is a very important function to sketch. So what we do here is, we will first sketch x squared plus 1, right? Let me first sketch x squared plus 1. It's a parabola, very easy, right? So there you go. We have x squared plus x. And we know this point here is the vertex at 1, correct?
Yeah.
Now, we will sketch the function e of x, which is 1 over x squared plus 1. It really means, what is the reciprocal of 1? Tell me.
1.
So that point will be common. And a reciprocal of very high number is
Very high number.
0.
Yeah, very.
The graph will be something like this. And you can easily see why. Let me just show you, right? So we'll take some values of x. Let us say the value of x is, let's say, minus 2, minus 1, 0, 1, and 2. And let's take the values of 1 over, let's say, first we write x squared plus 1. Is it okay? So x squared plus 1, if you write, then 2 squared is 4. 4 plus 1 is 5. 1 squared is 1. 1 plus 1 is 2. 0 is 1. 1 is 2. They are symmetric, definitely. And 4, correct? So we get those points. How about their reciprocals? Well, it'd be 1 over 5, 1 over 2, 1, 1 over 2, and 1 over 5, correct?
Yeah.
And you also notice that if y value approaches infinitely large for this function, then here y value is approaching 0, right? But positive, reciprocal function, correct?
Yeah.
And therefore, that graph is justified. This makes sense to you. You can see that the domain is all real numbers. However, the range is restricted. What is the range of this function?
It belongs to real numbers, but can't equal 0.
It is less than 1 also. So it is between, y value is between 0 and 1, but 1 is included. You get the idea. So that is very important question. We have figured out that rational functions could be continuous without any restriction on their domain, correct?
Yeah.
And could be restricted in the range as from both the sides. You get the idea? From both the sides, we have our upper limit of 1 and the lower limit not equal to 0, slightly greater than 0. Is that okay?
Yeah.
Perfect. So you have learned vertical asymptotes, you have learned horizontal asymptotes, you have learned holes. Now, what we are going to do is talk about oblique asymptotes. Have you heard about oblique asymptotes?
No.
Okay, so that'll be a great thing. Let's try to understand oblique asymptotes. If I have a rational function with numerator degree 1 more than denominator, then what happens? So in this case, the numerator degree is 1 more than the degree of denominator. Can you give me example?
Okay, for example, x squared plus 8 over x plus 1.
Good job. X squared plus 8 over, let's just keep x for now. Is that okay?
Yeah.
Simple as that. We can do x plus something. Now you see, degree of numerator is 1 higher. That means if I divide this, what will I get? Well, I could write this as x squared over x plus 8 over x, which is, as you can see, x plus 8 over x. Do you see that?
Yeah.
Now, what really happens when x is approaching positive infinity? Tell me, what happens when x is approaching positive infinity? Or even when x is approaching negative infinity? What happens?
The y value gets closer to 0.
No. So 8 over x, y value actually becomes closer to x. Do you see that? Because 8 over x approaches 0.
Yeah.
Do you
Oh
see
yeah.
that? Because in
Yeah.
this case, what really happens is that 8 over x, when x approaches infinity, 8 over x approaches 0. Is that clear to you? So
Yeah.
this term approaches 0, so the function approaches x. If x is positive, it approaches positive infinity. If x is negative, it approaches negative infinity. Does it make sense to you?
Yeah.
So now, if I have to sketch this function, how will it look like? So as you can see, it is x plus something, right? X plus something, and that x, even it is not x, but it is very close to x, correct?
Yeah.
8 over x is what you understand, is a reciprocal function, right? But
Yeah.
what is really happening is that at a value which is infinitely large, the function is approaching this line, which is y equals to x. Is that okay?
Yeah.
So let me sketch it on the next page. So what we learned now, that we learned about the oblique asymptote. It means as x approaches positive infinity, or when x, I should say and or. Is that okay?
Yeah.
Or negative infinity, y approaches a line. Do you understand?
Yeah.
Y approaches a line, then we have an oblique asymptote because the curve is approaching that line. You understand? So
Yeah.
we took up an example and we say, well, the function f of x, for example, is x squared plus 8, you said, over x, which is equals to x plus 8 over x. Correct. So
Yeah.
basically, it is 8 over x, but plus x, right? So a straight line also. So therefore, the function basically will look like this. Let me just focus on the line itself, which is y equals to x, correct? So this is my line y equals to x, which goes through the center, diagonal line, correct?
Yeah.
To sketch the real graph, in this particular case, I should take some values and make a table of values, correct?
Yeah.
Of course, if x is positive, in that case, my value will be more than this, right? If x is greater than, look here, let's take some values and we can just make a table and then we'll figure it out. Is it okay? So for
Yeah.
different values of x, I will take x plus something. Is that okay? X
Yeah.
plus something means more than x, right? So if I take a value of x, which is, you clearly know it cannot be 0, right? Because that is a restriction. So we know 0 is a vertical asymptote. 0 leads to vertical asymptote. Is that okay? So
Yeah.
at the center, let me draw a vertical asymptote indicating that it cannot be passing through the 0. Is that clear to you?
Yeah.
First. Now, it will go through 1 plus 1 minus 2, something like this, right? So let us now substitute some values. If I put 1 here, then what do I get? 1 plus 8, which is 9, correct?
Yeah.
If I put, if I put, let's just say, well, I put 2 here. In that case, 2 plus 4, 6. Is it okay?
Yeah.
Let me put minus 1 now. Minus 1 means minus 1 and minus 8, which will be minus 9, right?
Yeah.
And if I put minus 2 and minus 4 means minus 6. It does have a symmetry, right?
Yeah.
So as you can see, the plus and minus values are like negative. So it has kind of an odd symmetry. We also see that it is approaching, and if it is on this side, it is approaching from above, right? Why? Because the function is x plus something, right? So more than
Yeah.
x. On this side, we will see that it is approaching from down because x is negative.
Yeah.
Because now it is x plus 8 over x still, but x is less than 0. So minus, right? X is a negative number. So it is moving below. And therefore, it is kind of like this. So if you plug in the values, you will find that this graph will look like this. Do you see that? And symmetry. I mean, like this. Do you see that?
Yeah.
That is how this function is going to look like. And you can actually draw this function by taking many different values. Correct? For example, take values of x as half, right? Minus half. 1/4, and get some more values, right? Close to 0. Because this portion, which is a curved portion, there you need many points, correct?
Yeah.
To get it accurate. If you put one part, then the other part is symmetric. Right?
Yeah.
Perfect. Now, you understand now how do we get an oblique asymptote? Degree of numerator is 1 higher than the degree of denominator, and so you get oblique asymptote. Perfect?
Yeah.
Now, with that, we have learned major concepts about rational functions and its discontinuities, right? So let me write discontinuities of rational functions. So one, we discovered whole, right?
Yeah.
So that is common factor. In numerator and denominator. Clear?
Yeah.
Second, we discovered okay, I wrote vertical asymptote. That means denominator is 0 with no common factor. Is that clear to you? And then we covered oblique asymptotes. And here we say the degree of numerator is 1 higher than that of the denominator. Clear? So
Yeah.
these were the discontinuities which we talked about. They are all dependent on the numerator and denominator factors. Are they same? Then they cancel away, leading a whole. If the degree of numerator is higher, in that case, we have an oblique asymptote for sure. 1 higher means it approaches a line. But if it is 2 higher, it will approach a parabola. You get the idea?
Yeah.
Not a line, but a parabola. Right. And if the denominator is 0, but it does not have a common factor in the numerator, in that case, we will have a vertical asymptote. Perfect. With that, let's have now a few questions where we will also involve horizontal asymptotes. Correct? So now, in the questions which I am writing, what you need to figure out is you tell me the equation for horizontal asymptote. Vertical asymptote, oblique asymptote, and holes. Is that clear?
Yeah.
First question. If I have a horizontal asymptote, can I have oblique asymptote also?
Um, no, because it's like a line. It can't like go over the horizontal asymptote.
No. It is no, the answer is correct. However, the reason is not correct. Reason is that you have horizontal asymptote if and only if the degree of numerator is less than or equal to that of denominator. Correct?
Okay.
If degree of denominator, I mean, if the degree of numerator is higher, then you have oblique asymptote. So there are two contradictory conditions. They cannot exist together same time, correct?
Yeah.
Let's have examples. So this is what you have to fill in with each example. So example mx is 2x plus 1 divided by x squared. Tell me, what is the horizontal asymptote for this particular function?
Okay. Horizontal asymptote is y equals 0.
No, horizontal asymptote. Yeah, y equals 0, correct. Vertical asymptote. Yeah,
Okay. 0.
x equals to 0, correct.
Yeah.
Oblique asymptote, not valid.
Yeah.
Poles, none.
Uh. Yeah.
Another function, n of x equals to n, x plus 1 over x square minus 1. Tell me.
Okay. The horizontal asymptote is y equals 0.
No, it is coefficient. See, in this case, I could write this as x square plus x divided by x square minus 1. For example, do you see the degrees are same? When the degrees are same, then the horizontal asymptote is ratio of the leading coefficients, correct?
Yeah. Okay.
So y equals to 1. Next, vertical asymptote.
Okay. X equals to plus or minus 1.
No, one of the factors cancel because the numerator could be factored as x plus 1 and x minus 1, correct?
Yeah.
So one of them cancels, and therefore there will be a whole also. And the whole in this particular case will be at the cancelled factor x plus 1, which is x is equal to minus 1. Do you see that?
Yeah.
And the vertical asymptote will be at x equals to 1. Is that okay?
Yeah.
You get it? And when you have a horizontal, you cannot have a oblique asymptote. Now, let me give you oblique asymptote example. P of x is equals to x plus x squared over x squared plus x cubed. Tell me, for this particular function, what is going to be the asymptotes? What is going to be the whole, if any? How will you do this?
Okay. Think the horizontal asymptote is there is no horizontal asymptote.
Correct. No horizontal asymptote. Correct.
Okay. The vertical asymptote I think is x can't x equals 0.
Now look here. Very interesting case. I take x common from the numerator, correct?
Yeah.
Then what happens? Let me take it on a fresh page, okay?
Yeah.
X plus x squared plus x cubed over x squared. Very interesting, okay? Let's clear this. So we're saying that we have a function p of x, which is like x plus x squared plus x cubed over x squared, right? Now, if you try to simplify, you can take x common, 1 plus x squared plus 1 plus x squared, correct?
Yeah.
Divided by x squared. So the only restriction here is that x is not equal to 0, correct?
Yeah.
Now, once you cancel, we do have a common factor, but still the restriction is that x is not equal to 0, correct?
Yeah.
So at this point 0, what do you have? Do you have a whole or do you have vertical asymptote?
Uh. Think you have a whole.
No, because x cannot be 0, but it is still exists. It is still exists there. So that means as the function is approaching x, it is approaching a value which is infinitely large. You get the idea?
Yeah.
So the only difference in case of a whole, it is approaching a real value. And for an asymptote, it is approaching infinitely large value. Do you see that? So that
Yeah.
distinguishes whether we are going to have a hole or we are going to have an asymptote. So when there is a struggle, I mean, both the conditions are being satisfied. In that case, it will be vertical asymptote, correct?
Yeah.
So because now if you plug the value very close to 0, 0.0001, you will get a very high value, correct?
Yeah.
You will not get like last time we got some value 2, 3, 4, some real numbers. No, no, no. We are getting very high value. So in this particular case, which very clearly you can now write the function p of x as x and x cancel. So we have 1 over x plus 1 plus x. Is that okay? And definitely x is not equal to just 0. It has a vertical asymptote for sure. Is that okay?
Yeah.
Now, we know that it has oblique asymptote also. Can you tell me the equation of oblique asymptote?
Uh, x squared plus x plus 1.
Do you see? 1 over x is your rational function, which is approaching a line x plus 1. Do you see that? So the
Yes.
oblique asymptote is y equals to, you can write x plus 1 or 1 plus x. Do you see that?
Yeah.
So that is how you have to figure out where is the oblique asymptote, right? And
Yeah.
of course, if you graph it, practice graphing, look at you can also just use graphing calculator just to visualize how these graphs will look like and then try to sketch them. So we have a line which is x plus 1. This is the oblique asymptote. We do have vertical asymptote. Therefore, the graph will be now again like this. Do you see? We saw this graph earlier also, correct?
Yeah.
Now, it is possible for me to put y equals to 0, right? Because if I write this side as 0, we can find the x-intercepts, right?
Yeah.
And we, so you could solve for it, writing 0 here and find the value because you have a function there, right? So cross multiply and see. Do you get zeros, right? So you can figure out, does your graph go like this or it is below the x-axis? You get my idea?
Yeah.
Perfect. So basically, I'm saying that this output is 0 means x 1 x times 1 plus x square is 0, right? Now,
Yeah.
if x square plus x plus 1 is 0, then what is b square minus 4ac? Well, b squared, b is 1 minus 4, so no real roots. Therefore, it is not having any x-intercept. So it will be like this. Do you see that?
Yeah.
So it will not have any x-intercept. So you can figure out the points and work it out. Is it okay?
Yeah.
Okay. Now, with that, we have actually covered almost all the critical parts of our rational functions. We have understood that a rational function may have a discontinuity, may not have a discontinuity, right?
Yeah.
So, can you give me an example where the rational function will not have any discontinuity?
Will not have a discontinuity?
Yeah, no discontinuity.
Okay. I think like x plus 1 over 2x plus 4.
2x plus 4 will be 0 for x equals to some value. So the denominator should be a function which will never be 0. For example, it could be x squared plus 4. That is never 0, right? Now you
Yeah.
write anything you want on the numerator. You get the idea.
Yeah.
So this means no discontinuity, right?
Yeah.
Here, x belongs to real number. Is that correct?
Yeah.
Okay. Now, one condition we learn. Second important thing we learn is there could be functions where we could have a factor being cancelled, right?
Yeah.
For example, we have, for example, x plus 1 whole square, right? Now, if I put only
Yeah.
one x plus 1 here and x minus 1, in that case, one of the factors will cancel. But still, another factor of the same kind is still in the denominator. It will lead to only vertical asymptote, not a whole. Correct?
Yeah.
So here, factors are cancelling. Factors are cancelling. And we are writing this as x minus 1 over x plus 1. The restriction still is only x is not equal to minus 1. And here we have no whole, right?
Yeah.
What a vertical asymptote. Does it make sense? So our earlier definition that whenever the factors cancel out and the denominator is 0, it leads to a whole is incorrect. So if sometimes the question is this statement always true, sometimes true, or never true? It is sometimes true. Is that okay now?
Yeah.
You understood? So it's a very critical question. We normally think that if there is a common factor between numerator and denominator for a rational function, then at that point we will have a whole, which is not absolutely correct. It is sometimes true because if we have another factor of the same kind in the denominator, that will lead to vertical asymptote, correct?
Yeah.
And the difference between a whole and a vertical asymptote practically is that whole approaches a value. However, vertical asymptote approaches infinity, which is not a real value. Is it okay?
Yeah.
That is what here. So at this stage, I will conclude our lesson on rational functions, talking about wholes, asymptotes, whether they are vertical, oblique, or horizontal. Correct? I like
Yeah.
you to now summarize today's learnings, right? So
Yeah.
recall, we are just removing the screen from here and not tell me. Start telling me right from the beginning what are rational functions and what have we learned about them.
Okay, so rational functions are a quotient of polynomials,
Mhm.
and we learned how to like determine the vertical asymptote, horizontal asymptote, and one special and a couple of special case scenarios like wholes. It's when there's a common factor in the denominator and the numerator, and they can cancel out.
Yes.
So
Completely. They can
yeah,
cancel out
so
completely. No other
completely.
remains, right? Yes.
So it leads to a whole.
Mhm.
And then we learned about oblique asymptote is when the degree of the numerator is like higher than the
One higher.
denominator.
One
One higher,
higher linear. Two higher quadratic. Do you understand?
yeah,
But by default, when I say oblique, we mean a line. Is it okay?
yeah,
One higher. Okay. Continue. Yes.
yeah. And then we learned how to graph oblique and like rational functions that have holes and how they look like.
Correct. Perfect. So if I tell you that I have a rational function whose vertical asymptote is at 3 and horizontal, I mean, when I say 3, you understand, x equals to 3 and horizontal asymptote is y equals to 1. Can you tell me the equation of this graph?
Okay.
So let's get back to the whiteboard. And you have to also say, is there only one equation or there could be many?
Okay.
So my question is, vertical asymptote is x equals to 3. Horizontal asymptote, what did I say? Y equals to
I think you said one.
1. Okay, 1. Tell me, equation.
Okay. So okay. On the denominator, I got x minus 3.
Vertical asymptote, yes, x minus 3 in the denominator, perfect.
It can be anything, but I just got x minus 3.
Good, good.
Okay,
And the
then
numerator, horizontal asymptote is 1. Then
yeah, so okay, and then on the denominator, I got
so clearly you could have many equations, right? You can even
yeah,
write here ax. Let me write down. A times x. Is it okay?
yeah,
Right. Because if I write a times x, in that case, a has to be 1, right? Because I have got x equals to 1. So a has to be 1. Okay. Let me not write x now. It could be x plus b. So if I write x plus b, in that case, clearly, I meet the condition, right?
Yeah.
Because now so we have a set of, so we have many functions, right? Because this b will lead to many functions, correct?
Yeah.
But if I define that my y-intercept is at 5, then I'll have a specific function, correct?
Yeah.
So this leads to a family of curve, right? However, if I define a point P, which is the y-intercept in this case at 5, now I know that the point 0, 5 exists. So in that case, what will I do? I'll put 5 here, and then I say x plus b over x is 0 for me, right? So 0 plus b and 0 minus 3, and I can find that the value of b is minus 15, correct?
Yeah.
That becomes specific equation, and now I say y equals to x minus 15 over x minus 3 is the equation of this particular graph which I've drawn there, correct?
Yeah.
So with this, you have learned one more thing, and that is many times just by knowing the vertical and horizontal asymptotes, we actually get a family of curves. They have the common horizontal and vertical asymptotes. But if we specify any other point on the curve, any other point, then we are specific and we are talking about a particular equation representing that particular graph. Is this clear to you?
Yeah.
Perfect. So that's a nice place to end. So we'll end our lesson at this place. And I hope with this you get fairly good concepts in your mind and you can use these concepts in the class as they move along. Perfect?
Yeah.
Okay, then. Have a good night.
Okay. Bye.
Thank you. Bye.